In this video, we are going to explore how we predict where an equilibrium will lie. In other words, which side will be favored in an equilibrium, in a system at equilibrium. And we're going to look at the two factors of enthalpy, which is noted by H, and entropy, which is noted by S. Okay, so we'll start by reviewing enthalpy. In chemistry, the concept of enthalpy is basically a lot like heat, but it also is, technically I think it's heat at constant pressure, but it basically also tells us a lot about the potential energy of the system. So for an exothermic system, of course, we're going to compare the exothermic case to the endothermic case. These are the two options. And we know that in any chemical reaction, there is a temperature change. There is an energy change, and there's an internal energy change. So we could basically look at this like potential energy on the y-axis, or we could look at it as like H on the y-axis. But if we have a situation where the reactants start at a certain level, and then we know a reaction progresses something like this, and then the products are at a lower level, so what we've seen is a decrease in enthalpy or a decrease in potential energy. That's the case where it's exothermic, okay? So what has happened is that energy has been released out into the surroundings, okay? And what we often observe in the macroscopic setting for what we can observe with our senses is we will observe a release of heat. We would feel this reaction get hot, okay, because it would be releasing energy to our hands or to the surroundings or to whatever, okay, but it would be decreasing in potential energy or decreasing in enthalpy. If we extend this concept to the endothermic case, okay, so we look at the potential energy or we look at the enthalpy in the endothermic case. If the reactants started here and then the reaction progressed and the products ended up here, we would have a net increase in enthalpy, okay? And this would be the endothermic case, right? Now the products would actually be higher in potential energy than the reactants, and what would happen is energy would need to be kind of absorbed or sucked in order to make this happen. All right, so just a quick review of what goes on with enthalpy. And then alongside that, we have this concept of entropy, okay? Entropy, denoted by the symbol S, is generally speaking a measure of disorder and randomness, okay? So what this looks like is that we have this natural law, I forget which one it is, or law of thermodynamics or something or other, but there is a law in the universe, let's say, that basically the change in entropy always increases. Okay, so things fall apart, things move to a greater, or things have a tendency to move to a greater state of disorder and randomness. What does this like practically look like? Well, it means like whichever state is broken apart the most, or I should say maybe whichever condition has the most pieces is broken apart the most, or has the most pieces, that's going to be favored, okay? So what that ends up looking like is something that's a solid actually has less entropy than something that's a liquid, which actually has less entropy than something that's a gas. So we can draw this kind of little chart like this where we see an increase in S as we go from solid to gas, okay? So practically what it means is that whichever condition has more gas particles, it's also going to have a greater entropy. So basically, more gas, more entropy. So in other words, like naturally in the universe, systems will move naturally to a more gaseous state because that's considered to be more disordered and have an increasing amount of randomness. And if you think of the way the particles behave, we know, or you should hopefully remember, that for gases, they have the most freedom, essentially, to rotate, to translate, to move around, and they are the least, the least compacted, and the least dense among all the states of matter, and so they have the highest amount of entropy. Okay, so the big question, like, what does H and S, what is enthalpy and entropy have to do with chemical equilibrium? Well, in general, chemical systems want to minimize enthalpy and maximize entropy. What does that mean? It means that they prefer a situation like this, where we see entropy decrease, because that way products will be more stable than the reactants, or vice versa. They want to choose, systems want to be in a more stable and lower potential energy state if they can be. And then in terms of entropy, they would much rather be like the situation with the green molecules on the right, a lot of freedom and in their gaseous form, as opposed to very rigidly condensed into a structured and orderly solid, or a liquid where they're forced to be close to each other and don't have that much freedom. Okay, so let's try and apply this practically. So I've written the balanced chemical equation at the top here for a certain system, and I'd like you to pause the video and try and evaluate this system based on entropy and enthalpy, and let me know which side do you think would be favored at equilibrium. Do you think there would be more, it would more like favor the left and there'd be a lot more stuff in the reactant side, or do you think it would favor the right and there would be a lot more stuff on the product side when this system is at equilibrium? Okay, if we have a close look here, so if we're looking for the enthalpy factor, if we go from left to right, does enthalpy increase? Well, what we see is we see the energy value here, okay, which means, as you hopefully recall, that this is an endothermic reaction, okay? So it's endothermic in the forward, and we're always going to talk like in the forward, okay? So this would be an endothermic reaction. So in an endothermic reaction, remember the enthalpy actually increases. So in other words, like, since it's endothermic in the forward, that's not very favorable. Remember, we don't want systems to move this way, okay? Because this is more unstable than that original position. And so it would not be favorable to lie in the forward direction. Having a look at, so that was kind of looking at enthalpy. So if we look at entropy, where do we see the most freedom? Where do we see the most gas molecules? Well, that in this case, let me maybe use a different color here. We see the most gas molecules on the left, right? So what that means is that entropy would decrease. This would decrease in the forward direction. Okay, and so that's also not favorable. And so, by and large, the answer to this is it would lie to the left. It would lie heavily to the left. As a matter of fact, so it would lie heavily to the left, or we could say it would favor the reactants. And you could maybe even go so far as to make the statement that this reaction might not happen at all. So rather than being in chemical equilibrium, basically it might actually just look like this, okay? It would entirely exist as reactants. The other thing you could say is it might not proceed at all. So we could write that statement. We might say this reaction would not proceed, or we could maybe say, I don't even know how to spell proceed, like that, I think. This reaction would not proceed, or there might be no reaction. We could also say that. Okay, compare that previous example to this example and do the same thing. What do we think about the enthalpy? What do we think about the entropy? And where do we think this equilibrium would lie? Would it lie to the right or would it lie to the left? So looking at enthalpy, we can see that we have the energy being released here, which means that it's exothermic in the forward direction, okay? And exothermic in the forward direction, remember that means that the products are going to be lower in energy than the reactants, which means they're more favorable. So that's a good thing. This means they're more stable, and so that's favorable. It's a good thing. If we look at entropy, we would see that on the left side, we have one gas molecule, but on the right side, we have two gas molecules, okay? So that means that S would increase, entropy would increase as we went to the right, which is also a favorable condition, okay? So we have conditions favorable moving forward for both enthalpy and entropy. So in this case, it's the opposite of the last one. We would expect this equilibrium to lie to the right, or we might even make the statement that we would expect this to go 100% to completion. So it would lie heavily to the right. It would lie heavily to the right. Or we could say it would favor the right or the products. All this is just, I'm just trying to remember different ways to say the same thing. So it would lie heavily towards the products, heavily favor the products. It would go to completion. You hear this stated sometimes. It would go to completion, or it would go 100% to completion. All of these things would be correct predictions. And again, these are just predictions. It might change a little bit on a case-by-case basis. And speaking of a case-by-case basis, let's do the same on this one. Let's look at the enthalpy, let's look at the entropy, let's try and predict if this would favor the right or favor the left. So, in terms of enthalpy, there's the energy there. So we know this is exothermic in the forward direction, which we know would favor the products, okay? We know this is going to favor products. If we look at entropy, we see we would have 2 and 3 gas molecules on the left, and we only have 2 gas molecules on the right. So actually, entropy would decrease as we go forward, and that is not a favorable condition, okay? So what do we predict for this one? Well, we would basically predict that this one must lie in equilibrium. So, you know, we don't exactly know which side would be favored, but we would predict this system will exist in chemical equilibrium. Will exist in equilibrium. So these features of enthalpy and entropy, they help us make an educated guess about whether products or reactants will be favored in a system.